So yesterday, we started talking about the unit circle and non-unit circles and the coordinates based on the circle using which trig ratios. What trig ratios were we focused on yesterday? Sine and cosine. Yeah, sine and cosine yesterday. Okay? And we were talking about, let's see what you guys remember about yesterday. Lights. We were talking in here. Oh. All right. So if I have this circle, let's say this is a unit circle. Okay. And I draw an angle here, theta. And I want to find x and y. What did we say yesterday we can do to find x and y? Right? Yep. We said yesterday that x was the cosine of theta and y was the sine of theta. Okay? That's what we said yesterday. Then we went and said, what if it's not a unit circle? What if all of a sudden I went up here and said, oh, this is not a unit circle. This has a circle, a radius of r. So now we're going, oh, not unit, it's a r radius of r. How does that change this? Yeah, it just makes it x equals r times the cosine of theta, and y equals r times the sine of theta. Okay. Okay, now, I told you that we're kind of where we're headed with all of this. So yesterday at the end of class, we were looking at that London Eye problem, right? And we had created a table of values, and then we kind of made a hand sketch of it, right? So this right here, where's it at? Here's that. So this is kind of that sketch idea we came up with, right? Now, what I want to go ahead and do is, what if I said to you, hey, you're on this ride, and I want to know your height above the ground after, let's see here, oh, power goes off 26 meters or 26 minutes into the ride. Remember, it takes 30 minutes to go all the way around from the problem yesterday? And I said, I want to know if the power goes off after 26 minutes, are you going to be able to just jump to the ground or not? Are you close enough to the ground you can just get out? Or you have to wait for somebody to come get you? I want to know your height. The only way to do that is to try to write some function. Now, when I did this problem here, these are my input values. So my domain was an angle measurement, right? And my range, my output was the height above the ground. That's the way I graphed it, because that's what I did here with this table of values. Well, I would have to change this. And how would I change it? Because this was all about minutes, not about rotation. Now, if I go back here, I think I wrote it down for my other class. Here you'll notice I got t equals 0, t is 7.5, t is 15, t is 22.5, t is 30. That'd be minutes, right? 30 minutes for a full revolution. And I said, I want to know your height 26 minutes into the ride if the power goes off. You should be able to tell me what quadrant you're going to be in. You're going to be in quadrant 3, between 22.5 and 30. You're going to be somewhere in here. This is the area you're in. Now, boy, I don't know, how am I going to do this? Okay? So what we would like in the future would be to be able to write a function for this and graph it. Now, we're not there yet. This is where we're heading. As I said, I'm showing you a destination of kind of what we want to get to at some point. So this is what I was trying to type in yesterday and it wouldn't let me work for you. So here we go. So Go. So here is a function. Okay? So I want you to look at this. This is 0, 0. What does that represent? That's what? 0 minutes into the ride, you're at the bottom. You're 0 feet off the ground. What's this one right here mean? 15 minutes, you're where? At the very top of the ride, correct? This is what? After 30 minutes, you're back at the bottom. What does this one right here mean? 7.5 minutes, where are you at? Halfway up. So what position on the circle are you at? Which one am I at? If I start at the bottom, what? Give me like an hour. Think about a clock. What time am I at?
3 o'clock.
You're at the 3 o'clock position, right? You're where the positive x-axis would be. And then this would be at the 9 o'clock, and the negative x-axis. Now, I said I want to know, hey, the power goes off, and this right here, this 225, this is just called a midline. And this is something I just grabbed for yesterday to look at it. But I said I want to know, where are you going to be at 26 minutes into the ride when the power goes off? Well, I could, if I want, just kind of come down here and try to find it, and oh boy, 74.446 feet above the ground. Should you jump? Bad idea. Broken legs or more. Okay? As a matter of fact, I could tell you your height at any time that the power goes off. I could go ahead and say, oh, at 19.66 minutes, you're 351 feet above the ground. Now, the only way you can learn how to do this kind of a graph, which is called a periodic graph, and we're going to talk about that today, what the word periodic means. And this is also known as a sinusoidal curve, okay, is to understand the unit circle and the relationship between these positions and sign. Now, I'm going to just show you the function here, okay? There is the function. You'll notice up here it says y equals 225 sine of minus pi over 2 plus 225. Okay, so let's think about these numbers on here, just for the fun of it. Guess what this 225 in the front is? It's the what?
Radius.
It's the radius. Remember how we said you find it's r cosine theta and r sine theta? Now, since I was doing height, I'm only interested in the sine theta. So it's 225 sine. Oh, that's easy enough. So this is the radius. Sine, because I want to know the height, the y value. Now, this in here is a little more confusing, but this minus pi over 2 shouldn't be. Why is that? Because that's where we started at, minus pi over 2. I will tell you right now what this is. This is how I convert from minutes to radians. And I'll teach you that later on. And then guess what this 225 here's for?
That's to get it to 0.
What's that?
It's to get it to 0.
That's to get it to 0 because the center of the circle is not down at the bottom. It's up 225 feet. So each one of these numbers has a meaning in it. Okay? And this is where we want to get to. We would love to be able to get to the point where we could write a function like this and then use this function to solve. That's our goal always, is to learn something that we can apply later on somehow. And this is not the only type of problem we can apply this to. There's a lot of different functions that can be modeled using this technique. And we're going to look at those in the future. To get there, we have to do some other things first. Okay? So that's why we're doing what we're doing right now. There is a reason that we're going ahead and doing all of these things. Okay? Now, so before we go any further, is there anything from yesterday, though, that you wanted to ask about? Anything about these things or this stuff here? This is the r cosine. Is there anything from yesterday you wanted clarification on when you looked at it? No? You felt pretty good about what you looked at yesterday? All right. Well, then we're going to go ahead And we're going to move on. So today we're going to look at not two trig ratios, because we did that yesterday. We looked at sine and cosine, but we're actually going to look at a total of 6 trig ratios. Now you're thinking probably, what's 6? Wait a second. How many trig ratios do you know? 3. There's actually 6. We're going to talk about those today. We're going to actually define the new 3 that you don't know yet. What's the third one you do know that we haven't talked about yet? Tangent. Okay? So we're going to talk about those to start. And we're going to do that by using a circle again. Okay? And we're going to start with the unit circle. So I'm going to go ahead, draw a little unit circle here. There it is. Beautiful unit circle. Okay? Unit circle. And I'm just going to put a theta on here. Doesn't matter where I put it at, but it's easiest to start it in quadrant 1 for us right now. So I'm just going to put this one right here. Boom, there it is. X, Y. Great. Okay, here's theta. All right. So yesterday, this is what we did yesterday. Yesterday, I drew a right triangle like this. Here was X, here was Y, that was 1. And that was how we found out, by using right triangle trig, we found out that X was the cosine of theta, and Y was the sine of theta. That's what we did yesterday. Now, we just said the one we don't know is we haven't talked about yet that you know is the tangent. So let's talk about it real fast. What is the tangent of theta going to be equal to? If you're looking at the picture up here. Yeah, right. It'd be opposite over adjacent, so y over x. Correct? It'd be y over x. Fantastic. Hey, you want to know something really cool? Watch this. The tangent of theta is y over x. That means the tangent of theta is the same as the sine of theta over the cosine of theta. Look at that. You didn't know that, did you? In geometry, did your teacher ever tell you that? That the tangent was sine over cosine? It is. That's because you don't think of it that way in right triangle trig. Okay? We're thinking of it a little different perspective here. So right now, these are huge things that we now know. Okay? These two are from yesterday. This one's new. So tangent of the angle can be y over x, or it can be sine over cosine. And we did that because what? Replaced the y with the sine, and I replaced the x with the cosine down there. That's what I did. I substituted in. All right, that's nice. I like that. Good. So here we go. We're going to define the 3 new trig ratios. Okay? Now, when I write this, and I did that before, you guys all knew what that meant. From right triangle trig, you all knew the sine was opposite over hypotenuse, cosine's adjacent over hypotenuse, tangent opposite over adjacent. And we just used that knowledge here to write these things down over here. That's where those came from the prior knowledge that we had. All right, here we go. These are the new ones. Instead of SOHCAHTOA, it's this. JOSHIKEO. Now, what in the world does it mean? What I first want you to notice is I want you to look at these last 2 letters in these compared to the last 2 letters in these, and what do you notice? They're what? They're opposites. Now, what did this OH stand for? This stood for O over H. So what's that going to be? H over O. So what I'm really doing is I'm flipping all of these, is what I'm doing. The other 3 are obtained by flipping the original 3. All right? So the key is the first letter is just what we call the ratio. So here we go. This first one right here, this one is called the cosecant. It's abbreviated CSC, cosecant. All right? And the cosecant of an angle, I'm going to put an angle here, theta, would be hypotenuse over opposite. Now let's go up here. If I want the cosecant of theta then, it's hypotenuse over what? Wait, the hypotenuse is 1.
Y.
Oh, I'm sorry. Yeah, it's 1 over y. Okay? That's the first one. I'm going to come back to that in a second. We're going to add some. Actually, I'm going to do it right now. And if it's 1 over y, that's the same as saying 1 over what? Sine theta. So cosecant of theta, this is the same as that. Cosecant theta is the same as 1 over the sine of theta. All right, here we go. The second one here. S stands for secant. Okay, secant, and it's abbreviated SEC. And it's defined as hypotenuse over adjacent, which would mean it's 1 over x, which means it's 1 over cosine. This is equivalent to 1 over cosine. The last one down here, KO. It is the cotangent. And it is abbreviated COT. And it's going to be what? Adjacent over opposite. So up here it'd be what? X over y. Which means it's what? Cosine over sine. Guess what else it is? Cotangent of theta is also what do you think cosine over sine is? Think about it. If I flip this, I flip 1 over tangent. Whoa. So these are all the same. Now, those things are important because anytime you have something like this and you can replace it with this, that's nice. You know why? Your calculators don't do cosecants. Your calculators don't do secants. Your calculators don't do cotangent. But they do sine, cosine, and tangent. So you have to know these things over here in order to use your calculator maybe to find some value. All right? Now guess what? We call these identities. Okay? These are equivalent, but their identities look what? Different. We call them trig identities. Okay? We call these trig identities. So we're actually going to start a list of trig identities. What I just written here, we're going to kind of like just do a new page here of trig identities. All right, so here we go. Let's go back to this and add a page on here. All right, so what I'm going to do right now is given sine theta, cosine theta, and tangent theta. Those are the three we've started with, okay? Here we go. The first one is cosecant theta is equal to 1 over sine theta. This is called a trig identity. Very equivalent, but they look different. All right? The second one is the secant of theta can be replaced with 1 over the cosine of theta. They're equivalent, they look different. You see this, you can replace it with this, and it's completely correct. The next one is the cotangent of theta. We said the cotangent of theta is equal to what? We wrote it 2 different ways. One way of writing it would be writing it as 1 over the tangent of theta. We also said that the cotangent of theta is equal to what? Cosine of theta over sine of theta. All right? So these are things that we have just discovered. So we defined what these were, cosecant, secant, and cotangent. And then we see that they're really just what? They're inverted. They're not inverses, because that's a function term. You've got to be careful. They're the original 3 ratios inverted, is all they are. Okay? Now, guess what? If this is true, guess what I could put up here if I want? Let's think about this. If cosecant theta is equal to 1 over sine theta, what do you think I could say sine of theta is equal to?
1 over cosecant.
1 over cosecant. What do? Flip both sides. Invert both fractions. So that means that what? Cosine theta is 1 over secant theta. And what? This one's good. Tangent theta is 1 over, tangent theta would be 1 over cotangent. And we already know, what else do we know about tangent theta? We already said this, that tangent of theta is equal to, if I flip this, I flip, it's sine over cosine. So what we have right now is we have this list of things, which allows me to replace with equivalent statements that are true. Okay? If I see this, I can put this. If I see this, I can write this. If I see 1 over secant theta, I can replace it with cosine theta. If I see sine or cosine over sine, I can replace it with cotangent. If I see sine over cosine, I can replace it with tangent. I'm allowed now to start replacing things with equivalent statements. Again, these are known as identities. Now, these right here, I'm going to tell you, in case somebody says it to you. These 3 here and these 3 here, those are known as reciprocal identities. Because all I'm doing, what's reciprocal mean? Yeah, you're saying, what's it mean? To take a fraction and flip it. These are called the reciprocal identities. Okay? These are boom and boom. This one here and this one here, those are referred to as quotient identities. Okay? The tangent is the quotient of sine and cosine. The cotangent is the quotient, which means to do what? Divide. They're called the quotient identities. So you might hear something or read something that says, hey, using a reciprocal identity, or if it says using a quotient identity, those should mean something to you. Now, I'm not going to give you on a test and say, list the reciprocal identities. List the quotient identities. But I could say, hey, write down an equivalent statement to cosecant theta, 1 over sine theta. So these are things that you're going to want to start knowing. Okay? And there's multiple reasons you're going to want to know them. One of them is solving trigonometric equations later on, things we're going to be doing. Another reason is when we start doing, I told you guys we're going to do trig proofs in here, writing proofs. we do these things. It's called analytic trig. We do these proving things by using identities to replace. So that's something we're going to want to know. So you're going to want to know a lot of these identities and know what they say. All right. Now there's one other identity we're going to add right now. Are you ready? And I think we may have talked about it yesterday in this class. I don't know if it was this class or the other class. I did it in one of the two. So real quick, I'm going to just put a page here. And I'm going to draw a circle. And I'm going to draw this circle right here. And I'm going to say unit circle. Okay? Okay, great. And I'm going to draw a right triangle like I always do for you guys to help you out. Here's X, here's Y. All right, so who can give me an equation that I can write on the board that's true using Pythagorean theorem? This is a tough one, guys. Thank you. X squared plus Y squared equals 1 squared, which is 1, right? I could say X squared plus Y squared equals 1 squared, which is just 1. You guys agree with that, right? Now guess what? If that's true, and I know that X is the same as the cosine of theta, and I know that Y is the same as the sine of theta, guess what I can write? I can write that the cosine of theta squared, and I'm going to write it like this to start, don't write this down yet, plus the sine of theta squared is equal to 1. Now, you will not see it written like that. Now, here's what I want you to understand, okay? So I'm just going to come over here real fast. Side note. This. Okay, I don't want to write this with parentheses. Because if I write it with parentheses, this would this 2 apply to the cosine or to be applying to the theta? It's kind of confusing. If I write it like this is saying it only applies to the theta. I don't want to square the theta. I want to square the cosine of theta. So guess what I have to do? I write it like this. It's the cosine square of theta. This is the correct way of writing it. So when we see this, what we're now going to do is put, cosine squared theta plus sine squared theta equals 1. Boom. That's another huge identity. That is a hugely important identity. Cosine squared theta plus sine squared theta equals 1. So I'm going to go back and add it to my list I have here. Let's do it in purple. It's so important, it's royalty. Okay, and guess what this identity is called? The Pythagorean identity. Why? Because we used the what to find it? The Pythagorean theorem. It's called the Pythagorean identity. Okay? All of these things are going to be important for us in the future. All right? All of these are going to come back and we're going to start using them in here. Okay, so we got the original 3. We got the reciprocal identities to those. Then we had the reciprocal identities for the original ones. Then we have the 2 quotient identities in here as well, and the Pythagorean identity. Okay. So is there anything here that you want to ask about? I mean, this is not applied. This is just new things that we need to know. Basics, kind of, yeah. What's that? No, there's 6 of the, like, sine, cosine, tangent, cosecant, secant, and cotangent. These are the 6. Okay, as soon as you start flipping them, those are not new ones. Okay, so those are the 6. This is defined. These are defined as opposite over hypotenuse. These are hypotenuse over, adjacent over. So that's there's 6 original. Then when you start flipping them around, they start related to each other. Okay. Anybody else? Anything you want to ask, say? No? Okay. Woo! Feeling good. That's a lot right there. It's a ton. Okay. Good. Okay with that. All right. Quick coffee sip. Break here for a second. I'm going strong. Anybody lose power last night? You did? I lost it. 1 o'clock. It was off when I left this morning still. I don't know if it's back on or not. So, okay. Well, you're lucky if you didn't. I was glad to come to work because I could actually get some coffee. I couldn't even make any coffee no more. I was bumming. It was terrible. That was the worst part about not having power. No coffee. Wasn't the lights or anything like that. So, okay. So, let's go ahead and whoop, whoop. Okay. So here I've got a unit circle again. Keep using the unit circle. Why? Because it's nice when the radius is 1, right? That's always a nice thing when the radius is 1. Okay, so I'm going to put an angle up here that you should know. We all know that this angle here, if this is a 30-degree angle, is how many radians? Pi over 6. And we should know its coordinates are? Radical 3 over 2 and 1/2. As a matter of fact, let's just fill this in. I'm just going to put little marks where they're all at. Okay. And we'll just go around this. So this is 0. We got pi over 6, pi over 4, 3, 2. You come back and keep going. Take your break. If you don't, I will. Whew. I'll go outside and get a little fresh air.
No, this is only 20 grams.
That's why you're gonna be. Those technically count.
Yeah, Sam's is only 20. And it's 4 games.
What is it?
I don't know what's it called.
Do you not pack a lunch still? Get out of here. Oh, that one's good. So I go in the lunch line and whatever they have.
Every time I see Sam, I tell him what a nutritional lunch he has.
Is that just it? That's it. I mean, you know, I mean, free lunch. Everyone gets free lunch. I'm gonna go. Those are really good. You and my friends all.
And I give him a couple ounces.
It's real.
Told him to
Yeah,
say,
it must be that it needs something. Well, it depends on.
Where were you at? No, where were you at?
What lunch do you have? And he doesn't eat there. So I'm not. I have to study.
For my government quiz of the amendment.
I swear, if I had to, so I'll probably.
I forget all these.
The amendments.
I couldn't tell you a lot of them.
I remembered all of them for the quiz, and we had like a quiz on the amendments every other week, and I forget them between time periods. Like if
We had it every other week.
last time
That's not bad.
quiz, I got I got I went from 20, 3 out of 27 to 27. I haven't.
Yeah, we finished up with real quick.
Say that?
What?
Huh?
I did them all last night. It'll be like 2 hours. I was able to answer and then I was actually look for the other guy. I'm trying to put me there.
What? Oh. No. Is he so strong? It gets so funny without being funny.
Who is it?
He's really not gonna like it. That's like the I've never played that game. Yeah, I have games. Yeah, you know it's. Yes, you do. And then just training up for the rules. I don't believe him.
Hey, what are we doing in Spanish? What are we doing in Spanish?
What did we do? We did something at
Did you,
We did so the whole period. We did something at the beginning.
did you do like a quiz or something?
No, we watched the vid. Oh, we watched the music.
That's it?
Yeah, we
And-
did the music videos and we talked about like what they were about, and then we did grading homework for the rest. We don't do any learning in that class.
Oh, it's all
It's grading homework. That's all you do.
It's just Quizlet.
Yes.
What are you doing like that?
Yeah, I was at a different school the next day when I moved to another school. I started here. Dude, what do you do? Yeah, cool. Oh, my move. You went twice in a row. Sure. It was. You went for me. No, I don't even know who I was in that game. You know the strangers. Wow, maybe 23. Gosh. You got game night or something?
Remember when his parents locked his son?
Yeah. Oh, shut up. They still do that. Why is there? Oh my.
What'd you do to him?
I was just trying to turn up the volume, but nothing was happening. I couldn't hear it.
Brady wasn't good.
Don't like the word song.
Okay.
Okay. I just wanted to hear what was going on.
All right. Ready? Let's keep going here. So, let's get the ordered pairs up here. We might as well. Let's just, because we need this kind of. So, here the ordered pair would be radical 2 over 2, radical 2. This one you better know, right? Those are the guineas, right? Oh, I didn't put this one down. 2 down, negative 1/2. Writer's cramp. I'm writing so much today. All right. But that's okay. I guess we can do it that way. Okay, good. Woo! Great. I'm going to highlight something here. Actually, I'll circle it. So we got positive 1/2 here. We got a positive 1/2 here. Okay. All right. I have a question for you. So right here, if I circled this, this is just saying that the sine of pi over 6 is 1/2. Right? And here, this would be the sine of 5 pi over 6 is 1/2. Is the sine 1/2 every single time I have a pi over 6 of some type? Is it always positive 1/2? Every time I have a 6 in the denominator here is the sine of positive 1/2. No, it's not, is it? This is a negative 1/2 and this is a negative 1/2, right? Okay. So, when will this particular point repeat again? Like, give me an angle that you know has the exact same sine value as pi over 6. Give me an angle that you know must have the exact same sine as pi over 6. Pi over 6. Give me another one. And now you're going to crumble under the pressure. Give me another one. What? 2 pi plus pi over 6. Which would be what? Don't you hate that? Hey guys, little trick for you here. Are you ready? 2 pi plus pi over 6 is the same as 2 plus 1 over 6 times pi. It's the same thing. That's a mixed number. 6 times 2 is 12 plus 1 is 13. 13/6 pi or 13 pi over 6. Okay? 13 pi over 6. Boom. Got it. All it literally is it's a mixed number. And you use that idea how you go from mixed number to an improper fraction. Yep. So 13 pi over 6 is 1. What's another one? I don't want this. I want another angle in quadrant 1 that has the same as 1/2. It has the same sign as pi over 6. We got 1. It's what? We said pi over 6. The next one's going to be at 13 pi over 6. Where's the next one going to be at? What's that? 25 pi over 6. You have to add what? 12 pi over 6 over and over and over again, right?
Yep.
Yeah. So this repeats how often? Which is how often? Every 2 pi radians, this location repeats and this sign value repeats. How often when does this one repeat? When does this location repeat? Every 2 pi radians. When does this point repeat? Every 2 pi radians. When does this point repeat? Every 2 pi radians. Guess what we call that? When we get back to the exact same place we started at, and we know how long it takes, we call that the period of a function. A period is a what? Set amount of time, like a period of a basketball game, is a set amount of time. In math, a period is a set amount that gets me back to the exact same location. Okay? So if I write this down as a function, all right? If I write this down as a function, it would look the following. Because we're talking about functions. A function, I'm in a funk right now. A function, f, is said to be periodic. I'm going to just keep the eraser in my hand. If there is a positive value C, so that for every domain value of f, this will make sense as I get that, f of t is equal to f of t plus c. In other words, if I have an input and I can add an output to it and get back the exact same value again, that is known as a periodic function. Okay? That is known as a periodic function. Sine is a periodic function. Now, I'm just going to do this because it'll help you understand it a little bit better, I believe. So I'm going to go to Desmos real fast. And let's see what we got here. Start. And we're going here with this. I got to make sure I'm in radians over here. Okay, radians, and I'm going to set my x-axis to go from 0 to 8 pi. How many revolutions is that, by the way?
4.
Yep, that's 4 revolutions. And my y values, if I'm talking about sine and cosine, what does y stay between? What do the sine and cosine stay between? It goes think about the very bottom. What's the smallest y value you get on the unit circle? -1. The highest value is 1. So the y values are going to go -1 to 1. So -1. All right, beautiful. And we're going to have it step by pi over. This is all stuff you'll get to learn how to do. Pi over, I don't know. Well, I don't want that. No, I don't want that. I want to have the other one stepping by pi over. Pi divided by, let's have it go by 6s. Beautiful. Love it. Look at that. Isn't that beautiful? Look at that. Pi, 2 pi, 3 pi, 4 pi. Okay. So I'm just going to type in here f of x instead of t, it doesn't matter what it is, equals sine of x. Okay, so let's look at this. I want everyone to just kind of go through this with me because this is going to help us to understand a little bit what's kind of going on here. So I want you to look right here where I'm at, 0, 0. So of course this is 0 radians and the y value is what? 0. Okay? If I go up here, where am I at? pi over 2. I'm at the very top of the circle, and I'm at what? 1, right? If I were to go ahead and go through here, and let's say I go right here at 0.5, boom. Okay, when is the sign 0.5? That's not 0.5. Gotta go up a little higher. Well, may not let me stop there. What would that be at? When is the sign 0.5? At what? At pi radian? The sine is 1/2. When's the sine? When's the y value 1/2, guys? At pi over, isn't that the one I just did with you guys? At pi over what? 6, right? What's 3 divided by 6 roughly? 3.14 divided by 6. A little about 0.5. Notice where I was just, oh, no. I need to bring my keyboard over here so I don't have to keep going back and forth. Such a pain. Okay, so let's look at this. So right about here at 0.5, boom, this is that angle. So if you notice what's going on here, I want you to look at this graph. It goes down. Why are these down here negatives? Tell me where I am on the circle from here to here. Where is it? What part of the circle is this of this graph? This entire piece here is where on the graph? Quadrant 1. This is quadrant 2. Where's this at? Quadrant 3. Then I'm at. So I want you to look at this. Notice, see if it'll let me write. That's one cycle of the circle. What happens then? The graph does what? It repeats, and it goes and does the exact same thing. And then it does it again. Okay? And when I look at it, look at the distance between the repeating locations of the graph. In other words, how far is it from here to here? Well, where's this going to be at? Pi over 2. Where's this one going to be at? Remember, this is 2 pi right here. It's going to be at 2 plus 1/2, which is 5/2 pi. Is that what somebody said? I think somebody may have said. How far apart is that? 2 pi, right? Guess what? If I chose another point, I'm going to go ahead and choose one right here. Let's say I chose this spot right here. Guess what? Guess how far it is from this point to this point? 2 pi. If I chose this point right here, and I went over here and chose this point right here, the exact same location on that next cycle, guess how far apart those are? This is called the period of the function. It is how often it repeats. This is called the period. How long does it take before it repeats that exact same location on the circle or the exact same location on the graph? Okay? We call that the period of the function. So sine and cosine both have a period of what? 2 pi. So sine and cosine both have a period of 2 pi. Sine and cosine both have a period of 2 pi. Wish that would go away. All right, so I'm going to come over here. So sine and cosine both have a period of 2 pi radians. And that's the whole idea of coterminal angles. These coterminal angles get us right back where we started at. All right. Boom. So just understanding what this idea about to say, hey, the period of this function, I'm just telling you, this is how long it takes before it repeats itself again. Everything starts repeating again. Right? Okay, we have one last thing today we have to talk about. One last thing. Okay? Here it is. Now this is going to go back to a long time ago. Okay? Everybody in here should know what this is called. That is called the what? It's a quadratic, right? It's a parabola. Okay? If this is f of x. Okay? What do you remember about quadratics? Like, especially this kind here, like this one right here. Let's just say this is y equals 2x squared. Let's just say it's 2x squared. If I put in y equals 2 times 2 squared, where would I be at? Where would I be at? 8, right? This is 8. So if I went ahead and said boop, boop, here's 2, then this would be 8 roughly, we're saying. Okay? This is at 2, 8. Can anybody tell me what this point over here has to be? Negative 2, 8, right? You remember that? That's because quadratics had a line of symmetry, right? And it was just reflected across the line of symmetry, right? Now, so this right here, let's stick with me. So in other words, f of 2 equals 8. And over here, I would write that f of negative 2 equals 8. Okay? And that's true for all values of x on this function. Doesn't matter what I make x, it's true. In other words, f of x is equal to f of negative x. When that is true for all values in the domain, we call that an even function. We call that an even function, okay? So I'm going to write that down. If f of x equals f of negative x for all x values, f is called an even function. Boom. It's called an even function. All right, now let's go ahead and look at a different one. Okay? And you're just going to do this with me. So we just kind of looked at this as an example of what that might look like, that graph looked like, and it looks like this. We call it an even function. All right? Do we have it written down? Are we good? All right, go back to the other page. Actually, I can go to a new page. Doesn't matter where I go. Let's go back here. Okay, so again, I'm going to look at a graph. Okay? And this time I'm going to look at the function. We'll just call it f of x again. I'm going to call it f of x equals x cubed. Now let's real quick, we're just going to make a quick graph of this. We did polynomial functions way back when, a long time ago in a land far, far away. When you guys were all online with your cameras off and I didn't know who you were. So we're just going to graph this by hand real fast, just get an idea what this graph looks like. What would f of 0 be? 0, right? What would f of 1 be? 1. What would f of 2 be? 8. 1, 2, 3, 4. Okay? So it looks like it's going to go like this on this side, right? What about f of negative 1? Negative 1. What about f of negative 2? Negative 8. So it looks like this graph is going to go like this. Okay? There's this graph. Now, my first question for you is this. Would you say that this is an even function? Does f of x equal f of negative x? In other words, is f of 1 equal to f of negative 1? Is that true? No, it's not true. F of 1 is 1 and f of negative 1 is negative 1. So it's not true. So we would not call this an even function. Is it a function though? Yes. So it must be called something else. This is referred to as an odd function. Now, why? How do I know if it's an odd function or not? Here's how we know. Listen very carefully. Negative f of x is equal to f of negative x. Now look what that's saying, okay? If I took f of 1, what is f of 1? If I did negative f of 1, what would I get back? Okay, f of 1 is what? 1 multiplied by negative 1 is what? Negative 1. Boom. Okay, so f of 1 is 1 multiplied by negative is negative 1. Okay, now it's saying if I did f of negative 1, what's it equal? Negative 1. See how they're the same? If I did it for 2, it would also be true. What's negative f of 2? Well, f of 2 is what? 8. So it'd be what? Negative 8. What's f of negative 2 equal? Negative 8. See how they're the same? When that happens, we call that an odd function. Now, on the even function, the symmetry was where? On the y-axis. Okay? The symmetry here is through the origin. Because if you connect these 2 points, you will guarantee to pass through the origin. If I connect these 2, I will go through the origin. So odds are symmetric to the origin. Evens are symmetric to the y-axis. Okay? So over here, the second one is if f of x, I guess if negative f of x is equal to f of negative x for all x values, f is called an odd function. And again, we can write this down up here. This is, we can say it's symmetric to the y-axis. This is. And this is symmetric to what? The origin. Okay? All right, so are you ready? Let me grab this. Let's look at sine. I'm going to go back to my sine curve I had earlier. Good on time. We're doing good. Okay, so let me get rid of, oh boy, can I get rid of the writing hopefully? Where is, no, let's just start over, it'll be easier. I'm trying to figure out how to get rid of all that because it's not going to want me to. Okay, so here we go. We're going to look at y equals sine of x again. And I'm going to change this again real fast. We're just going to make this go from, we're just going to click it to radians. I don't have to set the window, doesn't matter. Great, get out of here. Okay, so I want you to look at sine. Here's the origin. Is sine an even function? Is it symmetric to the y-axis? Here's y. X equals 0. Right there, that is the, here it is. This is the axis of symmetry. This is the y-axis. Is it symmetric? Is sine symmetric to the y-axis? In other words, is f of pi over 2 equal to f of negative pi over 2? If it's symmetric, where should this point be at? Right over here, right? If it's an even, this is not an even function. It's a what function? Look at it. If I connect this point, this minimum, and this maximum, guess where I'm going to pass through? The origin. That means it's a what kind of a function? Odd. Sine is considered an odd function. Sine is an odd function. Okay? So we're gonna write that down in a second. What about cosine? Let's put, I haven't even graphed the cosine function yet. Let's do a cosine. Here we go. Y equals cosine of x. What's the first thing you notice, by the way, about these two things? What do you notice about the sine and the cosine curve? You notice anything about them at all? They look like they're the same, but they just kind of look like they're shifted, don't they? We'll look at that later on. Okay? There's a reason for that. Let's look at the green one here. I'm going to just turn this one off. Is cosine an even or an odd function? It's even. Why? Because it's symmetric to the y-axis. So right now, okay, we know that sine is an odd function and cosine is an even function. We're going to a new page here. So sine of x, in other words, sine of x is odd and cosine of x is an even function. Now, if this is true, if sine of x is an odd function, that means that what? Negative sine of x is equal to sine of negative x. That's what that means then. Okay? If this is an odd function, then the negative sine of x is equal to sine of negative x. If this is an even function, this guy over here, there we go, that would mean that the cosine of x is equal to the cosine of negative x. All right? Are we okay with that? Yes, no, maybe. Okay, so here's my next question for you. Knowing what you know about sine and cosine, and knowing what you know about the relationship of cosecant and secant with these, what do you think? I'm gonna put them here. If I talk about the cosecant of x and I talk about the secant of x, don't graph them. What do you think? Do you think that they're both even, they're both odd, that one's even, that's one odd? Do you know which is which? Think about it from what you know right now. Could you tell me and give me a reason why you think it is one or the other? Think about it for a second. What do you guys think? What do you think? Yeah. Cosecant is odd. You think that this is going to go up here, and you think this is going to go up here. Why do you think that? You're just talking about the reciprocal identities?
Yeah.
So you're saying since I could write this as 1 over cosine of x, and this would be 1 over sine of x, it should make sense that that's going to be true? Well, you know what? Let's just find out. Let's graph them. We're going to look at the graphs and decide if that's true or not. So I will do that. You're just along for the ride again. You're just paying attention here. Fortunately, Desmos will graph these. Okay, so here we go. So let's turn y equals sine of x on, and let's do its reciprocal, which would be y equals what? Cosecant of x. Okay, notice what it did. Does not support this. So how could I get past that? 1 over the sine. Yeah, see, that's how I have to get around. I have to know those identities to get around this stuff. Check it out. Look at this graph. Is that not funky looking? Now, notice, is it symmetric to the y-axis? No. It's symmetric to the origin again, which means it's a what? It's an odd function. Is that what he said? Did he say it was an odd function? Yeah, he said that. Let's see if the other one's going to be an even function or not. Let's go back to this. Here we go. All I have to do is turn this one into not a cosine, a sine, but a cosine. And what do I notice? Here's the axis. Oh my goodness, look at this. This piece of it right here is actually beautifully showing that it's symmetric to the y-axis. So it looks like secant is an even and cosecant is an odd. Okay, great. So secant is an even. I like that. Cosecant is an odd. Now, what does this mean? If this is true, I'm going to get rid of this and this. Okay? If this is true, that means down here I can write what? That the negative cosecant of x is equal to the cosecant of negative x. Why is that important? Because later on, if I see this, I could write this in place of it, and it's a lot easier to have a negative in front than a negative angle. Nobody likes working with negative angles. You'd much rather work with the positive angle. It's a lot easier in your head. This is beautiful to know. And then over here, what can we put? We can put that the secant of x is equal to the secant of negative x. And again, that's nice. If I see this, I would much rather think this. Again, I like dealing with positive angles if I can. These things are going to allow me to do that. They allow me to take anything that has a negative angle and rewrite it with a positive angle. And that is so much easier for you guys to mentally get your head around. We have two left. Tangent and cotangent. Tangent and cotangent. Okay? Now, let's think about this. Tangent and cotangent. I'm going to move this stuff here. Just going to give myself a little bit more room. What would it go? Okay. Alrighty. So, tangent and cotangent. What do you think? We know that both of these have cosine and sine in them, right? Well, I'll tell you what. Let's just look at the graph, and then we'll think about it algebraically if we want to. Let me just do a tangent of x to start. Let me do a tangent of x. Once we're done with these even odds, we're done, guys. Okay, so here we go. Let's just turn that one off. Whoop. And here I'm going to put in y equals tangent x. Okay, is it symmetric to the y-axis? No, it's not. Which means it's what kind of, is it symmetric to the origin?
Yeah.
Yes, so it's a what? Odd function. Let's make this a, you think it's going to take cotangent? I have to put what? 1 over the tangent of x. Even or odd? Is it symmetric to the y-axis? No, it's an odd. Both those are odd. Why? Because you've got an even and an odd together. That odd wins on that. Okay? So both tangent and cotangent go in the odd category up there. Both the tangent and the cotangent are going to go up here as well. Which means that I can add 2 more to this one. I can do 2 more over here. What do I know? I know the negative tangent of x is equal to the tangent of negative x. And I know the negative cotangent of x is equal to the cotangent of negative x. These are known as the even-odd identities. I'm sorry, yeah. Get that out of there. Put the wrong word in the wrong spot. These are the odd identities, and these are the even identities. And again, the beauty of these is you can take anything with a negative angle and rewrite it as a positive angle. That will be nice if we're solving equations and you have a negative angle in there, you can rewrite it so it's a positive angle instead if you want to. Okay? So this actually, these are identities. These are some extra identities, the even-odd identities. Okay? That's the last thing today. We have done a lot today. A lot today. Okay? So, hopefully you guys, and I still haven't heard back as to what's going on with the textbook thing, but hey, we got them right now, so that's good news for us, I guess. Okay? So I'm going to give you a little assignment to do over the weekend using the knowledge from today. This will be out of your book. Okay? Out of the book. So this is going to start on page 272. To page 272. I'm going to ask you to try the following problems for me. And I'm going to give you odds, because odds you should be able to check. So number 9, maybe try that one. Well, those, we already could do those, so I'm not going to worry about those. Boom. How about numbers 23 and 27? How about number, evaluate if possible, the 6th trick? Oh, I like that. That's beautiful. Number 35. We're going to wait on that and do those in class together. Oh, these are nice. Let's see here. How about number 49 and 51? There's no reason to even do that. That's it. That's it. A small assignment, actually. Okay? And you should already start trying to memorize some of the identities. The quicker, don't wait until the end to do that. Because when we start verifying trig identities, when we start doing the trigonometric proofs, if you don't know your trig identities, it's going to become a terrible ordeal. So you want to memorize them as we're going through them. You want to memorize them as we're learning them. That's the easiest way to stay on top of things in here. That's it. Boom. When you come back on Monday, we're going to keep on trucking. We'll look at these real fast and we'll keep on moving forward.